air will be stable if the adiabatic lapse rate, again, that's how quickly our particular bit of air cools off due to the change in pressure as it rises. If that's faster than the atmospheric lapse rate, then our air is stable. If the adiabatic lapse rate of our air in question has a low lapse rate, less than the surrounding atmospheric rate, then our air is unstable. Basically the idea here, if we have our air of interest and it gets warm, it starts to rise. If it changes its temperature slowly as it rises, it's still warmer than the air around it. That air is going to go right on up. If, on the other hand, we have air that changes its temperature quickly, warms up, starts to rise, it's going to just stabilize and stop. So the quick high lapse rate, air changes temperature quickly, means it adjusts fast, stabilizes. Low lapse rate, that air does not adjust well and remains out of balance, is unstable. It's kind of like reaction time. You can think of it that way. If you're driving, you're paying close attention, and you see something ahead, and you step on the brake and stop, you're good. If you're driving and on your phone, and all of a sudden, crash, you were not paying attention, your reaction time was bad, and you had problems. Fast reaction time, you did something. So, same idea here. You can think of your low lapse rate as being like a slow reaction time. That's going to lead to problems. Our fast reaction time, fast rate, adjusts, stabilizes. Moisture is our big difference here. Again, if we've got lots of humidity in the air, as that air rises, hits the dew point, now water's condensing. That releases the latent heat. In order for the water to condense, it has to release the energy it has as gas. That's going to keep that air staying warm instead of cooling off. And it's still warm, it's still less dense. So the wet adiabatic lapse rate is low. Now it depends on how much water you've got, things like that. But low, which means our more humid air tends to be unstable. Also, water heat capacity. Now steam is not as big a player as liquid water, but still makes some difference there. So our wet lapse rates are characteristically low. Typical wet air adiabatic lapse rate is less than the typical atmospheric lapse rate. The dry lapse rate is typically higher. So our humid air tends to be unstable, keeps on rising, and that keeping on rising is what builds our storms. Dry air tends to be stable, stops rising. So dry air adjusts quickly, high lapse rate, more stable, not likely to get a storm. Humid adjusts its temperature more slowly, so it's more likely to be out of balance, slow to adjust, unstable, and we get storms. With our air moving around, we can get a situation of temperature inversion. Hopefully you remember, down here in the troposphere, our bottom major layer of air, the air is getting its warmth largely from the ground. So as sunlight, if it makes it all the way through the air, gets to the ground, especially if it's close to straight overhead, so more of that's absorbed, less is reflected, and it's spread over a smaller area. If it's coming straight down, then spread out if it's at an angle. and it's going through less air. But at any rate, we warm up from the ground, air above it's warmed, and the further away you are, the cooler the air gets. Mesosphere, likewise, except it's the ozone layer at the top of the stratosphere rather than the ground that's our heat source there. However, warm air expands, it's less dense. So it will tend to move over cold, more dense air, and we can get a situation where we've got temperature inversion, as in instead of normally getting cooler as you go up, you've got some cool air under some warm air in the troposphere. Now, if you go all the way to the top of the troposphere, yeah, you're getting colder air all the way up there. This is a local exception to the general pattern. Called troposphere turning, it's dynamic. You do get these variations. Already mentioned, if we have a front coming in, either the cold front pushing the warm air up above it, or warm air sliding up above cold air, that can lead to an inversion there. Cold air, being more dense, can sink and get down into low areas. This happens often at night. You get cooler air sinking down into lower areas, valleys, and the like. Ocean, if that's cooler than the air next to it gets cool, and you can have temperature inversion there. Substance, again, cool air sinking down, different version there. Now, stable, not storms, but again, that can be a potential problem. City areas can have polluted air trapped. This is a photo of the Los Angeles area. Lots of people, lots of pollution, and you see that they have a temperature inversion, and the cool air that's stuck sitting over Los Angeles is icky brown looking. It's polluted. Then up above, you pass that, and we have the cleaner air beyond. Now, true, the source of this photo was San Francisco. They may have kind of enhanced the icky appearance to disparage their rival city, but shows that too stable air can get stuck. A classic example of that came back from the 50s in London. You had a very stable air mass sit over London, and hardly environmental regulation. Everybody's burning coal to heat their houses. Factories are burning coal for power, and all that smoke is mixing with the fog, and you had not only a polluted fog that was so thick that you had to have somebody holding a lantern walking in front of the bus to make sure the bus didn't run into something, but people with weaker health were killed in large numbers by the pollution trapped in this fog. And the government realized, no, this wasn't a good thing, and started to put some rules in decreasing pollution. Okay, so if we have unstable air, this can lead to producing storms. And so we'll look at a variety of possible causes, how they work. These are often concentrated along fronts. Now, fronts can be anywhere from weak to very strong. Some fronts, unless you were watching the Weather Channel, you wouldn't know that there was a front. Other times, it's a little windy out. Yes, there's a front. But that's all. But some fronts can be associated with severe storms. Weather has very important effects on us. If the link will come up here. There we go. A couple years back, we had 10 disasters that were causing over $1 billion of damage. These include a variety of storms, a series of tornadoes, various thunderstorm systems, a major winter storm here, flooding from hurricanes, another storm there. Drought and wildfire are not storms, but also weather related. Okay, so thunderstorm. That can be a fairly familiar sound around here in the summertime. Thunderstorms are relatively brief, but potentially very intense storms. Speaking of intensity, there. That's probably showing up a little better on the video. And so these are formed with our unstable air. Unstable air typically will be warm and wet, humid, moist air. Couple of major styles. Convective thunderstorm is when we have a patch of ground that gets extra warm compared to areas around it. Happens quite often on a warm summer afternoon this part of the world. And that warmer area, the air above it will be warmer. Maybe it's a little darker colored, has a lower albedo, whatever. So that warmer air is rising up, and it's pretty warm and humid. So it keeps right on rising up and developing into a storm. You get a great big puffy cumulus cloud that becomes our standard summer afternoon thunderstorms. Frontal thunderstorms, in contrast, form along a cold front. If the warm air in front of it is relatively humid, then as that cold front comes along, pushes that warm air up, rises quickly, quite unstable situation, makes storms, but instead of patchy clouds here and there, like our standard summer convective thunderstorms, this will be a line of storms all along the front, moving with the front. Frontal thunderstorms can occur any time of day or night, any time of year, whenever there's a cold front coming through. Even if it's already cold, you could have colder air coming in as a cold front and potentially lead to these storms if the air in front is sufficiently humid compared to what's behind. Again, air also rises if it goes over a mountain, and in doing so, you can potentially create storms with the air going over the mountains.